Hello again. Some of you may be viewing this after a 2-day break or whatever. I nearly went downstairs for a caffeinated soda, and I'm back to give you lecture 3. Normally I drink Jolt or Mountain Dew, so don't judge me poorly based on the substandard caffeinated swill that we have in the vending machines at DCL. Surge is not my drink of choice. So this lecture is going to be significantly smaller. The time for the pointer and memory lectures seemed to be much faster than I expected it to be now that I've seen it. And I guess that's because I don't actually have people interrupting me with questions. I will try and do a better job in these future lectures of anticipating the kind of questions I would get and responding to them and remarking on that. But we will see how that goes. There's always the temptation here to speed through the lecture with no one to stop you. And given my experience and the kind of questions I'll get, I will try and provide you with that kind of lecture experience in terms of here's a question that normally gets asked, but some questions are just unique from lecture to lecture, and so I really have no way of knowing what your questions would be till you get a chance to ask them. But that'll be the point of a chance when you get a chance to relate interactively with Charles or myself over the internet. So, in terms of dealing with arrays and strings, actually the lecture will just be on arrays, which is why I put strings in parentheses. There's some stuff in that third packet on strings, but the material basically is on arrays. Strings in this class are in C++ are very similar to arrays in that all they will be is arrays of characters. And there's various standard functions and such defined to operate on arrays of characters in both C and C++ as we're learning. But we'll tend not to use them, nor will we tend to really use arrays that much. What we're going to use instead, or you won't deal with them explicitly, we will use arrays quite a bit, and strings quite a bit, char array strings. But what we will tend to do is wrap them, and I have mentioned this near the end of the notes packet. The second section that you see Adam run through is going to be dealing with the idea of wrapper classes, which will be the idea of taking something like an array and having it as a member data, as an instance of a variable of a class in the same way that X chord and Y chord were instance variables of the chord class, member data of the chord class. And so the advantages this will gain us will be the idea of being able to add an interface, extending the interface of an array. Right now the array, as we'll see, is simply a tool to be used, some low-level language feature. By making it the member data of a larger class, when we allocate objects of that larger class, we will call member functions of that larger class. And those member functions then, their purpose will be to access this internal low-level array and do stuff with it carefully. And the user then can have, as the user uses the wrapper class, the array that wraps around the C++ built-in array, or the string class that wraps around the C++ built-in string feature, the char array strings, you will have the ability then to have various instance methods that are very carefully written to make sure they're correct, and then you can just call those with abandon. You won't need to worry about things like range checking yourself. The function will take care of that, or that wouldn't be the case in normal C++. It will be the case in Java. Java's arrays provide features like very clean error messages if you exceed the bounds of the array. They provide the idea of a length variable inside the array that you always figure out the length of your array. The built-in C++ tools are not like that because the built-in C++ array is not an object, it's not a class, it's simply a low-level feature. It's essentially pointer arithmetic, as we'll see as we look at the information I'm about to go over. And so, as a result of that, in order to gain some helpful features like range checking, like verification by the class that our index actually is within the range of the array, or something such as a size variable or a length variable so we can have the array tell us how large it is, we will need to have those as instance methods of a wrapper class, member functions of a wrapper class, inside of which is held the low-level array. So keep in mind that the stuff we talk about today is worth knowing, but you will very quickly cease to use a lot of it. You'll instead use the interface for a wrapper class, and Adam will go over both the string class and the array class that we'll be using for the rest of the semester, and those will hold respectively arrays of characters and generic template arrays. Both those will be low-level arrays. So the ideas you're seeing now, you'll see it pop up again in section 2, and then from then on we'll basically have array and string classes, helper wrapper classes that we will use, and the only time this stuff will show up will be the implementation code of those wrapper classes. That doesn't mean this isn't important, it just means it tends to be a little more error prone, and so we'll take advantage of our use of classes to make things a little safer for us in the same way Java did. If you want to tear all that away, you can use the lower language features, which are then not as safe, as we'll see, but also are faster. And so again, you've got that idea of you can always strip away things to make your programming faster, or you can keep the object-oriented features in to make things a little safer and easier and more maintainable and such. And usually that trade-off is worth it for us. Sometimes you'll need the speed, and that's how it goes. So, that said, let's turn our attention towards some actual code. So the first thing I'm going to mention is kind of a broad overview of what you essentially need to know to deal with arrays. The idea firstly is how Java dealt with arrays, to remind you of that if you have a Java background. And secondly, the two different ways in which arrays are dealt with in C++. That quick summary will be pretty much everything you need to know to use arrays. The rest of the discussion will be involving exactly how arrays work and give you some glimpse to the behind-the-scenes way in which arrays are manipulated. In Java, we have the ability to say, we have here an int array reference, call it x. And then we would say x equals new int, say 6 to get an array of size 6. And what we would then say is we could have things like x of 2 equals 5, or we have some way to print x of 2. And again, that's not legal print syntax in any language that we're dealing with, but I'm just printing pseudocode there. So that print pseudocode is just to indicate this is accessing the array cell for reading, where this line would be accessing it for writing. But that would be the declaration of an array reference in Java, the allocation of an array object for that reference to refer to, and then accessing an array cell itself for reading or writing. The indices, of course, went from 0 to 5, so there's your size 6 array, cells 0, 1, 2, 3, 4, and 5. Now in C++, we have a similar possibility, except we have 2 of them rather than 1. So in C++, we first have the idea of a local array, and the idea here is that we would simply say int x followed immediately by brackets and a 6. That one declaration gives us the array we need. We have simply said, here's our name, here's the size, we're done. The reason we don't need to do anything more is because this is not a dynamic allocation. We don't need to work the word new in there somehow because we're not allocating dynamic memory. This is just grabbed from the stack. What that means, however, is that whatever function this is written in, that array will go away once the function is over. Just like if we said int n, that n would disappear once the function was over. That is, the array here has the scope of the function. That's not something we were used to from Java, because Java arrays were objects, and so they persisted as long as we had references to them. Here we can have local arrays or dynamic arrays. When they're local, they have the scope of the function, and they disappear, they go away when the function's over. The usage syntax, however, is exactly the same. The array still goes from 0 to 5, and you use the bracket syntax to access for reading or writing. So the only thing that's really changed is the declaration syntax. In Java, you use those 2 lines. C++ local arrays, you use that 1 line, but the usage is exactly the same in both cases. So I'm going to write same here. Our other possibility is a C++ dynamic array, and this will, just as in Java, take 2 lines. We'll create a reference and then a dynamic allocation. However, in C++, of course, references are pointers. Java references are the equivalent of C++ pointers. So what we have here is integer pointer x, and then say x equals new int 6. Again, the usage syntax here is exactly the same. Use the bracket notation for reading or for writing to the array cell. You have array cell 0 through 5 if your size is 6. But the idea here is that these two lines form the array just as they form the array in Java. And what goes on here is, note, of course, Java had a special reference just for arrays. You had int with brackets after it, and that was your array reference. It was designed to say, well, now we've got the ability to refer to array objects. Here we have pointers. We don't have any special array reference. We have pointers to things, and so we have a pointer to an array, just like we have pointers to anything else. What this is going to mean for our purposes, though, is that there's going to be a very strong relationship between pointers and arrays. And we'll explore that for the rest of the discussion in this particular lecture. But aside from that, you've basically dynamic arrays in C++ and arrays in Java, which were only dynamic. There were no local arrays, are the same, essentially. This line's exactly the same, and here it's just a matter of, in C++, there's no specific array reference symbolism or symbols. So instead, we simply have an integer pointer instead. But the idea is the same as in both cases. X will hold the address of that dynamically allocated array. So the point here is that aside from the declaration/allocation syntax, arrays in Java and the two different kinds of arrays in C++ are exactly the same. This is the meat of things because you'll be accessing array cells far more than you'll be creating arrays. You create an array once and then use it many different times to access all the different cells, typically. So all that changes here is the allocation/declaration syntax. And so that's basically all you need to know in order to use arrays in C++. However, it's maybe not entirely satisfying in the sense that you'd like to know what's going on here and how it differs from Java in implementation. If you don't want to know that, well, you should want to know that because that's a noble academic goal. If you're just tired of hearing me talk, well, then you can, that's enough. But you really should know these details. So I'm going to be going over now basically the idea of pointer arithmetic and how arrays really work behind the scenes in C++. So let's consider our local declaration, where we simply say int x of 6. We have some memory diagram here. And unlike the last lecture, these are not pre-written, but we don't really need them to be in this case. Here, let's say we have A52, A56, A60, A64, A68, A72, A76, A80. And let's say that when we make this allocation, this local allocation, these are the 6 cells given to us, 3, 4, 5, for our array, for 0 through 5. So those 6 consecutive cells will be the array. They, of course, have to be consecutive. If no one's ever told you that before, I'm telling you now. The array cells, when you create an array, must be consecutive. And if you ever wondered why, we're going to see why in about 3 minutes. So we have here x of 0, x of 1, x of 2, x of 3, x of 4, and x of 5. And I'm writing all these array cell names in parentheses. Typically, as we've discussed and as I elaborated on a bit in that section 2 of the pointer packet, the second background section, when we have a variable, there's typically a mapping in the compiler between the variable and the memory location. In a sense, what we have here is 6 variables, 6 different array cells, but there is not a mapping in the compiler between each of those names, x of 0, x of 1, x of 2, and the array cells themselves. We don't want that set up like that, simply because there'd be an enormous amount of variable names. The whole point of using an array is to make one declaration and have it create a bunch of cells for us. Likewise, we don't want the compiler to have to deal with 10,000 variable names because we've declared an array of size 10,000. The array should be a small unit and not be taking up a lot of memory either in our program or while it's compiling. And so rather than map 10,000 different variable names in a 10,000 size array to different cells, what we will simply do is, no matter how large the array is, whether 10,000 or 6, all we're going to keep track of is the starting address, which here will be x. X is the starting address of the array. It cannot change. because it wouldn't make any sense to suddenly say, well, I'm going to magically move this entire array to a different chunk of memory. It's stuck here, just like when you say int n was at A48 at the beginning of that last lecture, and there it stayed. You couldn't just magically move n to a different variable cell. You could copy the value inside n to somewhere else, but you were not allowed to move n to a different cell. N was where it was. Same thing here with x. X holds the value A56. And so therefore, that's and I shouldn't have said the same thing with x. I should have said the same thing with the array. The x is holding A56. The array, therefore, can't be moved anywhere. The array is at A56. You can think of x as being a constant pointer, if you want. X doesn't really need to be stored anywhere inside memory in this case. Think of it as just a helpful compiler mapping to A56. You could certainly store it if you wanted to, or could it be stored. But the important thing is that A56 is dealt with in the compiler, and so you think of x as some sort of constant that can't change. The way you get at these various cells then is by having x. You have the starting address of the array. So each of these expressions then, x of 1, x of 2, x of 3, is really saying, and this is the key to arrays, x plus index times 4. And I'll explain why in a moment, but if you look at the cells, you see that that works. For example, if I want x of 3, I say x, which is A56, plus 3 times 4, which is 12, equals A68. And lo and behold, A68 is indeed the address of x of 3. So the question is, why does this work? And the answer is, the general way in which we access an array cell is going to be starting address plus the quantity index times size, make sure that's multiplication, size of type in bytes. So that's the equation here, starting address plus some offset, which is equal to the index times the size of type in bytes. Now, if you haven't seen this information in the beginning of that packet 2 yet, I'm going to remind you, or let you know if you're not knowing or don't know it already, that machines are byte addressable. That is, you have, say, a 32-bit word, a 32-bit memory cell, which is what we're assuming our examples are here in this class. And that would mean that you have 4 8-bit segments. And machines are generally giving you the ability to address memory in 8-bit segments. You can't address individual bits, but you can address bytes, 8-bit segments. So therefore, that's why we're skipping every 4th value here, or skipping to every multiples of 4 for our addresses, because this is really 53, 54, 55, and that's 56. So if we're only indexing words, they're going to be multiples of 4. It means, too, that since an integer takes up a full cell, it really takes up 4 bytes. And so that's where our 4 comes from. The size of an int in bytes is 4. And so here we're saying 3 times 4. That gives us the total number of bytes we skip. 4 for here at A56, 4 for A56, 4 for A60, and 4 for A64. And that places us right at A68, which is x of 3. The index comes into play because the index tells us how many cells to skip. If your index is 3, it's because you skipped 0, 1, and 2. If the index is 5, it's because you've skipped 0, 1, 2, 3, and 4. And so your index always tells you, we're counting from 0, how many cells you've skipped over. And if you take the number of cells you've skipped over, which is your index, times the size of each of the cells you skipped over, that'll give you the total amount of space you've skipped over. And add the total amount of space you've skipped over to the place where you started, and that will give you the place where you currently are. So A56 is where we started, plus 12 bytes we skipped over gives us A68. And that is how arrays are accessed in memory. When you deal with array access, that is what's going on, and so that is why arrays are constant time access. It doesn't matter whether we have an array of size 20 or 2,000 or 2 million. When we are accessing an array cell, all we need is one multiplication and one addition to get to that. So we don't need to step through individual cells, and so in an array of size 2 million, accessing cell 2 million and accessing cell 2 take the exact same amount of time. Therefore, access by index in an array is a constant time operation. It does not vary based on the number of data cells you have. So that's how the array memory works. Now notice again, you can't change x. X is a constant int. You're not going to be able to say, well, I want x to be A52 instead, because as I said, that would be the equivalent of sort of moving the entire array upwards one cell, and you can't do that. However, what you do have the ability to do is store x in different values. So what I can do here, grabbing another piece of paper, is to say, given that diagram, actually maybe I can just do this here. Given that diagram, I'm going to declare a new integer here. A new integer pointer called start pointer. And that will be down here. So here's start pointer. And what I'm going to do is say start pointer equals x. So start pointer here is going to hold A56. It's able to know what the value x is because we know x holds A56. That was in our compiler at the very least the address given to x to indicate our starting location. So we know x holds 256 even if it's not actually stored inside memory, and so start pointer can hold A56 as well. Now here's where things get interesting. Because of that equation, because of this equation here, starting address plus the index of the size times the size of the type in bytes, it doesn't matter what variable holds our starting address. I am perfectly able to say here start pointer of 3 equals 5, and the equation there will be the same. The address held in start pointer, which is A56, plus 3 times the size in bytes, which is 4, is 12, and that will write 5 into the cell x of 3. So notice what we did here. We took an array whose starting location was stored in x, and we're now treating the array as if its name is start pointer instead of x, simply by virtue of having start pointer and x hold the same location. So the actual array variable, the actual pointer variable holding the starting address of the array does not matter at all. Any pointer variable can be the name of the array as long as it holds the starting address of the array. And that's less important for local arrays. We don't really have any reason to do that. But for dynamic arrays, it'll be important because the idea is the dynamic array itself has no name. So we need to point to it with a pointer, and so the idea will be that just as in Java, a number of different array references could all refer to the same array, likewise in C++, a number of different pointers can all point to the same array. We won't be restricted to only having one specific pointer point to it. So we'll see that in just a second. Again, an example. Here we see an example where we're actually exchanging the name locally. And the reason this all works is pointer arithmetic. And this is sort of what ties local and dynamic and the original name and the new name together. The idea is that this bracket syntax is really the equivalent of dereference start pointer plus 3. This is what this is known as is pointer arithmetic. And pointer arithmetic, the idea is that when you add a pointer and an integer, the way that is interpreted by the system is that what you really want to do is say you want your pointer plus the integer times the pointer type size. And since start pointer is an integer pointer, for our example, that would be 4 as it was earlier. So that's the idea here, is pointer arithmetic means that when you add an integer to a pointer, what you're really doing is adding the integer times the size of the pointer. We're essentially saying then that that bracket notation is a shorthand for the pointer arithmetic, which is exactly what we want. We're saying all we're really doing is adding 3 cells of whatever size to a pointer. That's what it means to add an integer to a pointer, that we're adding 3 leaps of the relevant size to this pointer address to get a new address. And so that means then here that if I want the address of x of 3, what I need to do here is say start pointer plus 3. That will calculate out to an address, just as if I want x of 3, I then need to dereference. Getting rid of the address would be a dereference. Here I dereference that, and so that's why I would do this. Start pointer plus 3, and so if I want to say x of 3 equals 2, I say dereference start pointer plus 2. Or I'm sorry, start pointer plus 3 equals 2. That's how pointer arithmetic is. There's a few more examples in the notes you should take a look at. You don't really need to worry about pointer arithmetic. You definitely want to know how arrays are calculated, but the specific idea of it being pointer arithmetic in C++, don't really worry about too much. It's rarely used in C++. We're certainly never going to come back and look at it in this class, but it's helpful to know that information and at least be aware that this is really what's going on. But that's basically the idea here, is that this bracket syntax is equivalent to pointer arithmetic, and since any pointer could hold the starting address and this arithmetic would work out just as well, it means you can put the brackets after any pointer and have things work just as well. And so as a result, you can have any pointer you want refer to the array, whether the original name, x, which was a constant pointer, or a new variable, which is a pointer as well that will hold the starting address. Either one of them works just fine as a name of the array, because both of them are really involved in this expression. Even though we like to see it this way, this is really what's happening. And so that's why the pointer name doesn't matter. All that matters is what's stored there, namely the starting address that we're adding to 3, which is really an automatic adding it to 3 times 4 in the case of integer pointers. So that's what's going on there. And so we can refer to this array using x or using start pointer. As you might imagine then, dynamic arrays are really not much different. All that's going on here, if we look back at the original slide, is that here we have the dynamic array is simply going to set up a pointer x, and x will hold the address of this new array. So it's exactly like start pointer was locally. Namely that we now will have an actual variable that holds a starting address. Here we had the exact same thing. We had a local variable that held the starting address of an array. And now we're going to have a local variable that holds the starting address of an array. So at this point then, the only difference is what area of memory the array is allocated from. Is it allocated from dynamic memory, in which case you know the array will continue even though the x might disappear at the end of the function, or is it allocated from local memory, in which case you know that the array is going to be gone at the end of the function as well. But that's the only question. There's no other ambiguities between anything, because pointers and pointer arithmetic and array access with the brackets works the same way whether you're dealing with local arrays or whether you're dealing with dynamic arrays. And if you get nothing else out of today's lecture, that's what you should get out of it. That this idea of saying, as long as a pointer holds the starting address of your array and it's of the same type as your array, then that pointer can be the name of your array, because the system doesn't care about the name of the variable, it cares only about what the starting address of the array is. And so in this example that I had up on the earlier slide, here's x, and all that is, this is your memory here, and all that is the case is you have now a dynamic cell range. Here's x of 0 through x of 5, and if this is at a 10,000, then x will hold a 10,000. And I'm aware that diagram isn't terribly enthusiastic, but the point is it's exactly the same as before. The only difference is this would be in dynamic memory, so if it holds some sort of large address, that whatever that address is stored in x, and when I say x of 3, what I'm saying is the starting address, a 10,000, plus 3 times size of int, which is 4. And so a 10,000 plus 12 equals a 10,012. And if this is 10,000, x of 1 would be 10,004, x of 2 would be 10,008, and 10,012 would be x of 3. So it's exactly the same as we just went over, and I don't want to belabor the whole point again. It works the same way. The only difference now is the address array, the array address that x holds is now a dynamic array, not a local one. But that's all that's changed. The actual numerics of the accessing syntax work the exact same way. And that's really all there is to say. That's how dynamic arrays will be passed around. You simply have integer pointers to integer arrays or character pointers to character arrays. There's nothing else new. You're just passing around pointers to these arrays. And in fact, when we deal with the string issue, where strings are just arrays of characters, you will note that we'll always be passing around, or we would if we didn't have the string class, variables of type char star. That's in C and in C++ without a string class. That's one of your standard ways of dealing with strings, is to be passing around char stars. And now your functions are defined in terms of char star or character pointer, and so you pass in character pointers to the first character of every array. You'll hold the starting address of these character arrays, and that's how strings tend to be manipulated outside of special string classes, which we will look at. The only other thing worth remarking on is the delete operation. When you allocate an array using new, you have to delete it, of course, just like you had to delete things you allocated using new before, except with an array, since you have new with open and closed brackets, when it comes time to delete it, you need to have a delete with open and closed brackets. So if your new uses brackets and you're creating an array, you have to indicate you're deleting an array by using the brackets after the delete. If you just have a single object, then you just delete the single object as well, or call delete on a pointer to that single object. So that's your rule. New and delete go together, and new brackets and delete brackets go together. And that's really all there is to say about arrays. Like I said, look over the string chapter very brief, the small string section very briefly. But the rules are basically the same as arrays, except substitute character for integer in all these examples I've gone over. And there's different initialization procedures, but we won't be using any of them. We'll be using a wrapper class instead. So I could spend a lot of time talking about strings, but after the second class, it would all be moot. So I'm not going to bother with it, nor do I ever in any semester for this class. So I'm not just not bothering with it with you. I generally don't bother. It's in the notes if you want to take a quick look, but after second lecture, the string class we have there will be infinitely, second section, the string class we have there will be far more useful. So that's it. The next lecture, I don't think you ever see my face at all. That was the first one I taped. Not that you're going to be complaining about that. That is going to be discussing pointers and passing values to functions through the idea of pass by value and pointer and reference. So to deal with reference values and the semantics where we pass information to other functions, and there's a lot to talk about there, and so that will basically cover a regular lecture. I think it was about 46 or 47 minutes when I was done. So that will be that lecture. Lecture 5 will be on constructors and the big three. Lecture 6 will be very short on templates. Lecture 7 will be on inheritance. And so that's the roadmap for the next 3 lectures after lecture 4, because by the time you see this, lecture 4 will also be up. So the 2, 3, and 4 you now will have, and lecture 5, 6, and 7 I've now given you the roadmap for. After that, I have a little bit on abstract data types in lecture 8, and then we dive right into data structures. And that will be the data focus for the rest of the course. So we're about halfway through the C++ stuff now. See you next lecture. Take care.